this video we'll examine the technique needed to write the nth term of a geometric sequence. But before we just jump right into the formula, let's consider a geometric sequence real quick. So, of course, we have our first term. Get into my pen here. Here's our first term, our second term, our third term, our fourth term, etc. And this would be n, and this would be a sub n, of course. So let's think about this. We're here, we're 2, we're 4, we're 8, we're 16. I hope we can see the pattern. We're doubling it each time. So basically, to get from the first term to the second term, we're multiplying by 2 one time. I think we can recognize that r is 2. So basically, to get from the first term to the second term, we're multiplying by r once. And to get from the first term to the third term, we're multiplying by r, what, twice, right? And to get from the first term to the third term, I'm sorry, to the fourth term, we're doing the same thing. We're multiplying by r, what? 3 times. Or thrice. Yes, that's a real word. I promise you, maybe it's a little archaic. Now, that said, check it out. So, to get to the second term, you're multiplying by r 1 time. To get to the third term, you're multiplying by r 2 times. To get to the fourth term, you're multiplying 3 times. So in other words, you're multiplying by r 2 minus 1 times, 3 minus 1 times, 4 minus 1 times. To get from the first term to the nth term, you're multiplying by r n minus 1 times. And understanding that and getting a little bit of an intuition for that is going to be instrumental in understanding where the next formula comes from. So perhaps this is something to look back at once you've done a few examples of this and get some, like I said, to build some intuition for this. So the nth term of geometric sequence. Here's the formula for writing the formula. It's kind of an inception level formula. It's a formula to write a formula. Just like we use a formula to write the formula for an arithmetic sequence, this one is for a geometric sequence. A sub 1 still stands for the first term of the sequence. R, of course, is our common ratio. And n, of course, is our variable. And the n minus 1 portion of this, look back real quick. You're multiplying by r n minus 1 times to get to a sub n. You're multiplying by r. Repeated multiplication is what is the definition of exponentiation. So, that said, let's look at a few examples as always. We want to write the first 5 terms and then write the explicit expression for the nth term. That's a sub n. So here's it written recursively. Describing something recursively, super straightforward. We're taking the previous term and multiplying by 2. So in this case, the second term is 3 times 2, which is 6. The third term will be, yep, that's right, 12. A sub 4 is 24. And a sub 5, the fifth term, is simply 48. Okay, so to define it recursively, you're multiplying the previous term times 2. Now we want to take that recursive formula and turn it into an explicit one. So we've recognized there's our r. There is our r. R is 2. A sub 1, of course, we see it right here. It's 3. N is our variable. So a sub n is a sub 1 times r to the n minus 1 power. So, pretty straightforward. 3 times 2 to the n minus 1 power. Now, there is a little bit of playing around when it comes to exponents you could do with this if you really wanted to. This would be 3 times 2 to the n times 2 to the negative 1 power, which means you could rewrite this as 3 times 2 to the n over 2, which is also known as 3 halves, times 2 to the n. These would actually be equivalent expressions. Just, like I said, a little bit of exponent manipulation. But quite honestly, this is fine as a final answer. However, if you were to go and check an answer and see that it's this, you could hopefully be able to get from one to the other. Okay, so onward and upwards. Let's look at example 2b. Find the 15th term. Anytime we're finding a 15th term or something like that, we're definitely going to want to put an explicit expression rather than dealing with it recursively. First term, there it is 20, so a sub 1 is 20. Common ratio is 1.05, there it is, r is 1.05. And that's all you really need to know in order to write the rule. So a sub n is quite simply 120 times 1.05 to the n minus 1 power. So to find the 15th term, you would do 20 times 1.05 to the 15 minus 1 power. And, you see something crazy like this, you're probably going to want to jam that into your calculator. I know that I wouldn't want to do that by hand. So let's pull up the calculator, and we'll do 20 times 1.05 to the, I can do 15 minus 1, 14th power. And you get this, kind of long decimal going on, but that's where that number comes from, and that's what I would do every time with anything like that, would be to rely on your calculator. So the 15th term of this sequence is 39.5986, etc. And there you have it. It's not specified. You could probably, round this 39.6 or something thereabout. Okay. Let's look at one more. So we've got this geometric sequence. The 4th term is 125. And then the 10th term is 125 over 64. So, we have the 5th, 6th, 7th, 8th, and 9th term sitting in between 125 and 125 over 64. So what you got to think is you've done times r, times r, times r, etc. You've done that 1, 2, 3, 4, 5, 6 times to get from the 4th term to the 10th term. So rather than going all the way back to the 1st term, we don't need to do that. 125 times r to the 6th power has to give you that 10th term. So we're just going to do it that way. We're going to solve this equation. You could, of course, have gone back and figured this out, but we don't really know what r is. So let's solve for r. We're going to divide both sides by 125, or multiply by 1 over 125. So that goes away. We get r to the 6th equals 1 over 64, because the 125's cancel. And so we take the 6th root here. And so r is equal to 1/2. So we're not done yet. This is r. Okay? Now we need to go back and get the 1st term so we can write an expression for a sub n. Now you could say, all right, 125 times the 14th term would have to equal the 10th term times r to the 4th power. Multiplying by r another 4 times. Let's do it a little more completely. So we can work back here. Our Common ratio was 1/2. So this was 250, 500, and 1,000 for our first, second, and third terms. So our expression, our a sub n, is 1,000 times 1/2 to the n minus 1 power. I like to put fractions in parentheses like that, just for sake of ease in your notations. So you can now do a sub 14, the 14th term, is 1,000 times 1/2 to the 13th power. And let's do that right here, 1,000. Not 10,000, 1,000 times 0.5 to the 13th power. And hopefully we should get that mess, which, I don't know. Let's see if that's a fraction. Of course it is. So what you can see is the numerator is still 125, which is kind of nice. Because you're just multiplying the denominator by 1/2. So the 14th term is 125 over 1024, which, by the way, if you work your way through it, your a sub 11 is 125. Multiply this by 2, which would be 128. Your a sub 12 would be 125 over 256. Your a sub 13 would be 125 over 512, which brings us back around full circle to that. So we verified in a few different ways, but any way you look at it, the 14th term of that geometric sequence is 125 over 1024. And that is how geometric sequences work.